The first thing we're going to talk about is elastic potential energy. And the word elastic here just means springy, okay, or springs, okay? Things that are stretched or compressed. So things like coils, springs, I don't know another word for that, right? It's things that are elastic, things that bounce back and forth. So these are two terms that I just want you to be familiar with, at least. The first one, if a spring is static, what does that mean to us? It's just at rest. And then if it is compressed, it's pushed together. And if it's stretched, it's pulled apart, right? Those two terms sound familiar to us and comfortable with that? Okay. Tell me this, if we stretch or compress our spring, does it have potential energy? It does, right? Because it has the potential to do what? Go back to static. Bounce back, right? And get back to static, right? It will bounce back and it will transfer that stored energy into whatever it's connected to, right? If it's connected to something, it will transfer that stored energy into that object and make it move, right? Displace the object. It has the potential to do work, right? So if we look at potential energy, this is the potential energy of a spring. And so AP labels it as U spring, or an S.
We're not going to take into it.
All right, so the equation for potential energy of a spring is 1/2 kx squared. 1/2 kx squared. And that's a little bit of a new one for us. I need you to make sure we differentiate here that this is a lowercase k. It's a lowercase k. It's not representative of kinetic energy. The k is called the spring constant. Okay, it is the spring constant. And I wish I could say that constant actually means constant, but it doesn't. The spring constant is dependent upon the spring we're working with. Okay, it's a measure of basically how difficult it is to stretch or compress. So slinkies, very small spring constant. Suspension springs on your car, very big spring constant, right? We see the difference there. Really difficult to stretch or compress would mean a high spring constant. The unit for a spring constant is measured in newtons divided by meters. Newton divided by meters. Okay, the way that comes about is through this equation here, which we haven't talked a lot about. We'll get there later, but force is equal to the spring constant times x. So this is how we find that spring constant. The amount of newtons it takes to displace our object, the amount of newtons it takes to displace our object a certain number of meters is how we calculate the spring constant, right? How much force it takes to compress our spring 10 centimeters or whatever it might be. That's how the spring constant is calculated. So that's where that comes from. But it's newtons divided by meters. And that means that x is the distance that it is stretched or compressed, and it needs to be in meters. So that's usually one that we're going to have to convert, because we don't usually talk about compressing springs in meters worth of distance, right? Usually it's in centimeters or millimeters. So that might be one that we have to convert, okay? And then again, it's our x value that's squared, right? 1/2 kx squared. It looks really similar to our kinetic energy equation, doesn't it? 1/2 mv squared, but this one is 1/2 kx squared. All right, so now let's get into, we're going to work with springs a little bit more as we go, so we'll touch on that. But now we're going to look into what's called the total mechanical energy of the system. And we're going to start with perfect physics world, right, where mechanical energy is completely conserved, okay? And so we're going to talk about the conservation of mechanical energy. But mechanical energy is the sum of the kinetic and potential energy of the system at that particular moment. So mechanical energy is equal to kinetic plus potential. Kinetic plus potential. Okay, this is at one particular point in our system. Do you remember how the other day we kind of talked about kinetic and potential energy being like a pie chart? Right? If it has this much kinetic energy, then the whole rest of our system is considered potential energy. Right? And we looked at a roller coaster and said at the top of our roller coaster, we've got all potential. At the bottom, we've got all kinetic. And then anywhere between, we might have a fraction of each. But mechanical energy for a conserved system never changes, right? Whatever energy is contained in that system is how much it has the entire time. So that's our equation for mechanical energy. It's just the sum of kinetic and potential. So what this really comes out to is now when we're going to look at the conservation of mechanical energy at two different points in our system, we know that conservation of energy says mechanical energy of the first side is equal to mechanical energy second, or final, right? Mechanical energy initial is equal to mechanical energy final. Okay, so if we expand that out, that means kinetic plus potential equals kinetic plus potential, right? And so now this is just an expansion of that equation, right? This big one right here is what needs to go on your equation sheet. Okay, it's an expansion of kinetic plus potential equals kinetic plus potential, right? And the whole left side of our equation we would consider initial, and the whole right side of our equation would be considered final, right? This equation satisfies the law of conservation of energy for us. All of the energy at the beginning is equal to all of the energy at the end. Right? And these are for perfect physics world. This big equation is not given to us on our AP sheet, but it's one we're going to use a lot, right? We're going to be able to apply the kinetic and potential energy equations we know with this one. So this is one we're going to get really familiar with. Okay? Kinetic plus potential equals kinetic plus potential. Now, I'm gonna add one little wrinkle in here as well, because technically we have two types of potential energy, don't we? We have potential energy of gravity, and we have potential energy of a spring. So if we really wanted to be technical, we would put in plus 1/2 kx squared plus 1/2 kx squared on each side, knowing that we probably won't have all of these terms in every equation. Right? I don't even like to include that one, but I'm telling you that's the technical conservation of energy, is to have kinetic, potential of gravity, potential of a spring. But it'd be kind of rare that you'd have all three of those things, right? It wouldn't happen. So I'm going to lay it all out there for you, and then we'll walk through our problems and understand that normally we don't have all of these terms. Several of them are zero, and so we can drop them out of our equation. Okay? All right, the last little point on this says that just before an object hits the ground, we will consider all of its potential energy to have been transformed or converted into kinetic energy. So if we're talking about an object that's falling to the ground, as it reaches the ground right here, right, we're talking about like the instant before it hits the ground, how much kinetic energy does it have? We will consider all of that potential energy to be transformed. So if an object is at rest here, it would have all potential, sorry, I need to use the U, all potential. And down at the bottom, it would have all kinetic. And then we would have somewhere in the middle throughout there. Okay? All right, let's go ahead and try one here. Okay? Now, the problems that we're looking at right now theoretically could be solved using kinematics too. But I'm going to show you how to use the conservation of energy. And so from now on, we just have more tools to be able to solve problems. Okay? But for this one, I want to use conservation of energy to calculate it. So this says a stone is being held at a height of 3 meters. Calculate the stone's speed when it has fallen to 1 meter above the ground. So this is the 1 meter mark, 3 meters, and then here's the ground down here. Okay, so we need to kind of walk through here. What types of energy do we have? While our stone is being held or suspended, what type of energy do we have?
Potential.
This is all potential. And what type of potential energy is it? Is it spring energy or gravitational potential energy? All gravitational potential energy. And then at the end, as right here, what type of energy does it have? It definitely has kinetic. And what else? It also has potential of gravity. Now, this is gonna bother some of you, and some of you are gonna love what I say here. If I wanted to, I could reset the ground level to be right there. And I could say that my starting height is 2 meters, and I could call that the ground. And that would then take away my gravitational potential energy. Do you see what I'm saying there? I can kind of reset the ground level wherever I want it to be. That's really up to you. Does that kind of make sense? As long as you adjust your initial position. Which would you rather follow? Does anyone have a preference? Would we rather just reset our ground level? Yeah? Okay, so let's go with that. Let's go with what we have right here. So let's call this the ground level. That would mean that here we have all kinetic and here we have all potential. And that changes now our initial height to only be 2 meters. Do you see what I did there? Okay, so now if we set up our conservation of energy equation, we said, I'm going to just keep it simple right here. We said potential plus gravitational plus spring is equal to kinetic plus gravitational plus spring. But we get to exempt a bunch of these things from our equation, don't we? Because at the beginning, do we have any kinetic energy? No, so I can take that out. Do I have gravitational potential energy?
Yes.
I do. So now I'm going to plug in mgy because I know that's what it's going to be. Do I have any spring energy?
No.
No. So all of that gets to go away on the left-hand side. And I have all potential. On the right-hand side, what did we say we have? All kinetic. So 1/2 mv squared. These get to go away, right? So you see how we kind of start with this big scary equation and we're able to scale it down? All right, that's really what we're looking for here. So I'm going to plug in m times 10 times the height equals 1/2 m. And I'm looking for the velocity. Now, I've got an m on both sides. What happens with that?
Cancel.
It's going to go away. It's going to be canceled. Okay. So I'll take 20 divided by 1/2 and the square root of that. And I get a velocity equal to 6.32 meters per second. Now, would that velocity be positive or negative?
Negative.
Negative, because it's falling downward. It's in free fall. So I need to tack a negative on the front of there. Negative 6.32 meters per second. Now, I will tell you that most of the time AP asks for the magnitude of the velocity, which means we wouldn't necessarily need to include the negative, right? It might not give you that option to be negative in the problem. If it asks you for magnitude, it doesn't need to include direction. So that happens a lot with AP. But how do we feel about that? Pretty simple. Are we okay with this big equation, right? And then we just get to scale out what's not there, right? We take away what's not there. And if it's helpful for you to write in these plus zeros to know that, like, okay, I thought about them, but they're not there, you could do that if you want, right? But you don't have to. Okay, let's try another one. Assuming the height of the top hill of the roller coaster is 40 meters and the car starts from rest at the top, calculate the speed of the car at the bottom of the hill. Okay, so if we're at the top, our height is 40 meters. What type of energy do we have at the top of our system?
Potential.
All potential, and it's gravitational potential, right? At the bottom, what type of energy do we have? All kinetic. So we need to take our big equation. Kinetic plus potential equals kinetic plus potential, right? But I get to get rid of a lot of those things. We're going from all gravitational to all kinetic. So our setup looks exactly the same as our previous problem. Okay? M G Y equals 1/2 mv squared. Right? And like we said in our last problem, our mass is going to go away. Okay, mass is going to go away. So I'll cancel my mass. And I want to find my velocity. Did we end up with somewhere around 28 meters per second? 28.28, but I'm just going to keep it here for right now. Now, I will tell you that although our roller coaster is going downward, it's on a track, and so we just kind of consider that as forward motion. We can keep that as positive, right? It's not a free falling object. It's moving forward, so we'll keep that there at we'll keep that at forward or positive. Okay? Now, at what height will the car have half of the speed? Do we have an initial thought there? Is it going to be at the halfway mark? Right? That's the obvious thought, but let's solve that. Okay? Let's figure out at what height will it have half the speed. Well, what is half of our max speed there?
14.
We're looking for a position in which our object has a velocity of 14 meters per second. So that means we're really going to be looking somewhere in the middle, aren't we? Our cart's going to be somewhere in this range. Would we agree? It's going to be somewhere in there. We don't really know where, but it's going to be somewhere in the middle. And so when we look at this, we can still take our starting and compare it to our middle somewhere. So we're going to start out, we said, with only potential energy. And at the end, what type of energy will we have? Will we have kinetic? And we will also still have some gravitational potential energy because we're not going to be all the way to the bottom. And so we're solving for that final height. Okay, so mg height equals 1/2 m times 14 squared plus mg y, right? We're looking for what is the height. Do you guys have a preference right here about if that's a y or an h? Does that, if I accidentally mix it up, is that fine? Right? I know I usually like it as h, but AP puts it as y, so I don't want to confuse you. I'll try to keep it consistently at y, but it's just your height. Now, we've got m's all over the place, but we're going to be able to combine like terms here and work that out, okay? So this is 400 m equals 98 m plus 10 my. So that's what I got here for my height value, 30.2 m. Does that mean that it's rolled 30.2 meters downward, or is it at a height of 30.2 meters? What do we think? Has it traveled 30.2 meters down, or is it above the lowest point by 30.2 meters? Any thoughts on that? It's going to be 30.2 meters from the bottom. So that means we're about at this point right here. So out of our 40 meters of height for our coaster, we've only dropped 10 meters. Automatically, that has to do with this, right? Your velocity is squared. So it's not a direct relationship between height and velocity, right? It's exponential. So we're picking up half of that speed along the first quarter of our drop. So our height there is 32.2 meters. Are we okay with the algebra there? Are we feeling okay? Okay. What speed does the dart acquire? So let's kind of talk through what's happening here. We have a dart that is attached to a spring. Okay, the spring is compressed 6 centimeters and released. So it's going to, after it's released, the dart flies off. And the difference in these two springs right here, right, this difference from here to here is 6 centimeters. Can we kind of envision what's happening, right? It's like locked and loaded. And when it gets released, the spring and the dart detach exactly when it is at equilibrium, right? The spring is at equilibrium, okay, or static. Is that making sense? Okay, now what's going to happen is when that spring is compressed, what type of energy does it have? When that spring is compressed, it has potential of spring, right? It has spring potential energy. As it is released, all of the energy in that spring is transferred to the dart, right? And when that spring hits equilibrium, it's not doing anything anymore. It's not going to bounce back and forth, right? We're talking perfect physics world here. So all of the energy from the spring is being transferred to the dart. And what type of energy would the dart have then as it's moving? All kinetic, right? Because it's in motion. And the spring is at equilibrium. So there's no more energy stored in the spring. It's all being transferred. So we go from all spring potential energy to all kinetic. Okay? So again, if we set up our conservation of energy equation, kinetic plus potential equals kinetic plus potential. We have no kinetic to start, no gravitational energy to start. We just have spring, 1/2 kx squared equals all potential, all kinetic, no potential, no potential. All right, so on our spring side, we have 1/2. The K value is given to us in the problem, 250 times x squared. What needs to happen to that compression length? We got to put it into meters. So that becomes 0.06 squared equals 1/2. And then our dart, that's another cause for possible conversion, but it's already in kilograms. So we just got to be careful with that. Okay, so a lot of times those little tiny things would be in grams. So we'll say 0.10 times v squared. Okay. Oh, I didn't do something right. 0.06 squared times. So this gives me 0.45 equals 0.05 v squared. Okay, when I move that to the other side, I get 9. And so I think my velocity here comes out to be 3 meters per second.